Good morning. This is Neil Polhemus. I want to welcome you to today's seminar. We're going to be talking about a very popular statistical procedure that's implemented in Statgraphics. It's called cluster analysis. Cluster analysis has gained a lot of popularity recently because it's a technique that can be applied to big data in order to extract information. And it seemed like it would be a good topic to talk about today, and something that certainly illustrates the power of Statgraphics in terms of meshing analytics together with graphics. Now, I will invite you, as I usually do, to submit questions through the GoToWebinar facility. We'll be collecting those as I go here. And when I'm finished with my presentation, I'll answer as many of those questions as I can. All right. Well, what is cluster analysis? I looked around on the internet to try to find a good definition for it, and I found on businessdirectory.com the definition that you're seeing here. Basically, what cluster analysis does is it takes cases, observations, objects, whatever they might be, and classifies them, puts them into groups called clusters, such that items in the same cluster are very similar, but items in different clusters are different from one another. You can see the results of a cluster analysis in this graph here, where this is a famous data set having to do with irises, and based upon the petal width, the sepal width, the petal length, the procedure has taken something like 60, maybe 80 irises and divided them up into 3 groups. Okay, now cluster analysis is a discovery tool. It's really designed to show us associations, patterns, relationships, other sorts of things that might exist in a data set. And as they're indicating here on businessdirectory.com, it's often applied to very large masses of data. Now, I'm going to be illustrating the use of it on a smaller data set because it's a little easier for us to understand and to visualize what's happening when we have something without millions of observations to try to plot. Now, there are a lot of important applications of cluster analysis. It's widely used, for example, in market research, where the goal is to take your customers and divide them into different market segments based upon various characteristics, variables, and so forth that you know about those particular people. It's also used in medical imaging to identify different types of tissue. I've seen an application in bioinformatics where they take sequences and divide them into different gene families. Again, you can see the idea in all of this of forming groups of similar observations. There are applications of cluster analysis in social networking, where you divide people into communities. There's an application, several applications I've read about in educational data mining, where you take students and divide them into groups according to the different needs so that you can help different types of students. And finally, it's even used in climatology to identify similar weather patterns that occur on different days. Now, the data set we're going to be looking at today is a data set that comes from the World Bank. If you've seen some of my webinars before, I've looked at this data set before. It's freely available on the internet from the World Bank. I'll be looking at data from the year 2009. It's data on something like 175 different countries around the world. And what we know about each of these countries is various demographic information, such as life expectancies, fertility rates, infant mortality, that sort of thing. There are also economic variables in the data set, GDP per capita, inflation rates, and things like that. The goal of the analysis that I'll be doing today is to take these various countries and, based upon the measured variables, divide them into groups of similar countries. Now, starting out, I don't know how many groups there might be, logical groupings, nor do I know which countries belong in which groups. But it's going to be the goal of the cluster analysis to identify for us groups that naturally divide these countries into countries that are similar to one another and countries that are considerably different from one another. Okay, now as usual, I'm going to start by loading the data into Statgraphics and taking a quick look at it. So let me move over, if I can, to Statgraphics, where I've loaded up the World Bank data for 2009. And I've started by generating a matrix plot. A matrix plot is always a great way to look at multivariate data on multiple variables. If you haven't seen the matrix plot before, what it does is it takes all pairs of variables, and I'm actually going to be looking at 10 different variables today, and plots scatter plots, two variable scatter plots of each variable versus each of the other variables. So for example, one of the variables that we'll be looking at to define clusters of countries will be the logarithm of the population density. The log of how many people per mile there are on average per square mile in a particular country. Well, across the top, we see the log of population density plotted versus the rural population versus the female percentage. Again, read up to see what it's plotted against. Log population density versus the age dependency ratio, which is the percentage of dependent people, very young people or very old people, over the percent of the population that's of working age. We see plots versus life expectancy, fertility rates, the log of infant mortality, the percentage of GDP that's represented by trade, the log of the GDP per capita, and the consumer price inflation. Now, if you look throughout this graph, you'll see that there are certain variables that are very highly correlated with each other. For example, here in this particular plot, you see the relationship between life expectancy and fertility. Fertility is the number of children per woman on average in a particular country that a woman gives birth to. And there's definitely a negative correlation between life expectancies and fertility. On the other hand, you see a lot of variables that don't have much correlation. At the same time, you can see on the diagonal of the matrix a standard box and whisker plot for each of the 10 variables. And the reason I've taken the log of certain variables, for example, down here, the log of GDP per capita, is to make the distribution across the countries fairly symmetric. It turns out there are order of magnitude differences in GDP per capita amongst the various countries. It's much more effective in terms of coming up with an application of pretty much any multivariate technique if you try to make the distribution of a particular variable somewhat symmetric before you start. You can also see some fairly dramatic outliers. Up here you see actually a plot of female percentage, and there's one country in the world, Qatar, that has a very, very small percentage of females. I believe they bring a lot of males into the country to work. And you'll see actually that the cluster analysis will fairly quickly point out some of the outliers in our data set. Okay. Now, we need to go back here to our presentation and talk a little bit about the math behind cluster analysis. Okay. I'm going to start by using a little bit of notation here to represent the data we'll be working with. Basically, what we have in that World Bank data set are n multivariate observations. And we have a total, I believe it's 141 countries that have complete information on the 10 variables that I want to look at. And we can represent the data by a data matrix, where each row of the matrix represents one of our n countries, one of our 141 countries. Every column of the matrix represents one of the 10 variables that we have information on. The goal of the cluster analysis will be to use these multivariate observations to take the data and group them into clusters, where a cluster will consist of countries that have similar values for these 10 variables. Okay, now to do a cluster analysis in Statgraphics, what we're going to do is go to the multivariate section of the program. Now before I do that, I'm going to call up the data input dialog box for my matrix plot and just do a Control-C to copy the names of those variables. Then I can go to Describe Multivariate Methods Cluster Analysis, do a Control-V, and I've got the 10 variables that I want to look at. Okay. I'm also going to use the column called Country to label the individual observations, which will help me identify what points belong to what countries. Okay. When I press OK, it will show me the various options I have in Statgraphics for doing a cluster analysis. Now let me go back to PowerPoint for a moment, because I've summarized what the various options are in Statgraphics when you want to do a cluster analysis. First off, we have a choice of what we want to cluster. Do we want to take and divide the data into groups of observations, or do we want to divide it into groups of variables? The most common thing is to cluster by observations, which means I would take and create groups of countries, which is what I'm going to do. But it's also possible, if you have a lot of columns, that you might like to group the variables into groups, into clusters. Okay, same methodologies are applied, but you come up with groups of variables instead of observations. The second option I have when I do a cluster analysis in Statgraphics is what method I want to use to do the clustering. Now we'll see in just a moment that there are two major types of clustering algorithms. There are what are called hierarchical methods, and then there's the method of k-means. The first 7 options here, nearest neighbor, furthest neighbor, and so forth, down to Ward's method, are what are called hierarchical methods. In that case, we'll actually begin by putting every country in its own cluster and start combining countries that are similar until we get down to a small number of clusters. The only difference really between those first 7 methods, as we'll see, is how they define the distance between 2 clusters in deciding which clusters to put together. A slightly different method, but also a very popular method, is something called the method of k-means. As we'll see in the method of k-means, you begin with k seeds. You pick 3, let's say, very different countries. And I'm going to pick, for example, the United States, China, and India. Then you start matching other countries to those seeds. And after going through a number of iterative steps, end up with groups of countries, again, that are similar to one another. Okay. Now, we also have to tell the program, tell the algorithms, how to measure the distance in the multivariate space of the observations. As I'll show you on the next slide, we have 3 choices in the way we measure distances between multivariate observations. We can take and use a squared Euclidean distance. We can use a Euclidean distance or a city block distance. It's going to affect somewhat what countries end up being grouped with one another, but those are the 3 choices. We also can tell it how many clusters we would like to end up with. In many cases, we'll have it go all the way down to a single cluster and then look at when different countries were grouped together, or we can tell it to stop when we get 3 clusters or something like that. Okay. There's also an option here, a checkbox labeled standardize. If you check that, as I will, before it tries to measure the distance between observations in multivariate space, it will standardize each of the variables. And by that I mean it will subtract the mean of each variable from the observations and divide by the standard deviation. That's important if you have variables that are measured in different units, have different magnitudes, and so forth. Otherwise, the variables that are large will dominate the algorithm. Okay. Now, a little bit more about how we measure distance between observations. Let's suppose we looked at 2 countries, country X and country Y. And if you like, you can think of each country as being a point in a 10-dimensional space. I have 10 variables that I've decided to use for the cluster analysis. So X is a point in 10-dimensional space, which is a little hard to visualize. Okay, but it's like a point in 3-dimensional space. It's just in 10 dimensions. And then we have a second point Y also in 10-dimensional space. To define the distance between point X and point Y, which will be very important when we decide what points are similar to others, what countries are similar to others, we could use a Euclidean distance. This is the way we would normally think in 3-dimensional space of calculating a physical distance between 2 objects. Simply take and sum up across our p variables the difference between the observation, jth observation, jth variable for observation X, and the jth variable for observation Y squared. A standard measure of distance that you'd be used to in a 3-dimensional space, only extended to 10 dimensions. If we take the square root of that, that's typically called the Euclidean distance. Well, actually, this is the standard distance. The squared Euclidean is the distance squared. We can also think, though, of calculating the city block distance. If instead of taking and squaring the differences between each of the variables, we take the absolute value, we get what would be the equivalent distance between 2 objects if you were in a city and had to walk up one street and down another street. Couldn't, fly between the 2. So it's called the city block distance. So that'll be one of our important choices. Now, as far as the methods for doing cluster analysis in Statgraphics, I told you there are two. The first is typically called the agglomerative hierarchical method. In the agglomerative hierarchical method, you start by putting in each country into its own cluster. So if I have 141 countries, I start with 141 clusters. I then take and I find the two countries that are closest together using whatever distance metric I've chosen, and I combine those two countries into a single cluster. Okay, so now I have 140 clusters. I'll then go and look at the 140 clusters, try to figure out what clusters are closest together, take the ones that are the closest, combine them, and continue combining clusters until you get down to however many clusters you want. Okay, and the number you want may often be 1, but it could also be something bigger than 1. Okay, now the second method for doing a cluster analysis is to do what's called the method of k-means. In the method of k-means, you begin by creating k clusters using selected observations as seeds. So for example, and what I'll show you in a moment, I'll take China, I'll take the United States, and I'll take India, and I'll use them to seed my clusters. I'll then assign all the other observations to whichever country they're closest to, most similar to. So I'll then have 3 big groups of countries. But I won't be finished yet. Then what I'll do is I'll calculate the centroid of each of the clusters and check all of the points in the 3 clusters. And if there are any points in certain clusters that are closer to other centroids, then I'll move a point from one cluster to another. Okay? Now, let's start with the agglomerative method. The agglomerative method has a number of different choices. One choice, the default choice, is what's called the single linkage method, or the nearest neighbor method. Now what happens with single linkage is you start with n clusters, 1 for each observation, 1 for each of your countries. Okay. You then calculate the minimum distance between all pairs of points that are located in different clusters. Right? So you take a point in one cluster, a point in another cluster, calculate the distance. Now at some point there might be 5 points in one cluster, 10 points in another. You find the nearest neighbors, or the points in the 2 clusters that are closest together. Okay? Then what you do is, for the pair of points that are closest to each other across all clusters and all pairs, join together the 2 clusters that have the pair closest to each other. Okay, you then repeat that process, steps 2 and 3, until you get the number of clusters down to whatever number you want. Okay, that's called the nearest neighbor method. Now, it is a hierarchical clustering method, and there are a number of others. There's a complete linkage method, an average linkage method, centroid method, median method, Ward's method. The only real difference between the nearest neighbor method and these other methods is how they calculate the distance between 2 clusters. For example, I said in the nearest neighbor, you find the pair of points in different clusters that are closest together. And you call that the distance between the clusters. In the farthest neighbor method, what you do is you take all pair of points in different clusters, find the 2 points in different clusters that are farthest apart. That distance defines the distance between the clusters. Or you can find the distance between the average distance between pairs of points in different clusters, or the difference between the centroids of two clusters and call that the distance between the clusters. The centroid is actually the point in p-dimensional space located at the mean of each of the p variables. Or you can look for the distance between the medians, or you can use Ward's method. Ward's method defines the distance between two clusters in terms of how much the sum of squared deviations around the cluster mean would increase if you put two clusters together. Okay, now in choosing the method, what you'll see in just a moment when I do this, the most important thing will be how good an explanation it gives you of how these countries are related to each other. Okay, at least that's what I typically do. I try different methods, look at something called the dendrogram, which we'll see in just a moment, and based upon how things have been grouped, decide which method works best for a particular data set. Okay, and as we'll see in just a moment when I go back to Statgraphics, there are lots and lots of different options for output. And I'm going to try to show you pretty much all the output we get from the cluster analysis. Okay, so let's go back to Statgraphics for a moment. And I had gotten to the point where I was going to select a particular type of method to use. Well, I'm going to take all the defaults. I'll take the nearest neighbor method, squared Euclidean distance, standardize the variables, and have it go all the way down to a single cluster. And I'm going to ask it for all of the output. Okay? Now, what will happen is an analysis window will come up, as it typically does in Statgraphics when you run an analysis, and you can see some of the different plots that we'll be looking at, including the first one that I'm going to look at here, which is the dendrogram. Okay, now there's quite a bit of data here, so I'm going to change the font size. Actually on the x-axis is what I want to do. I want to go to x-axis, tick mark font, and change the font size to 4. What that's going to do is that's going to reduce the labels down along the x-axis, which are the country names, so I can read them so they don't overlap so badly. Okay. Now there is a very, very important plot in a cluster analysis. It's something called a dendrogram. It shows you the distance between different points when they're combined into a single cluster. Now remember, in a hierarchical clustering algorithm, you begin with every point, every country in a different cluster. You then find the two countries that are most similar and group them together. And you can see down along the bottom that there are lots of countries that are combined together at very small distances. Now you may not be able to read it, but if you look down here, very early on in my cluster analysis, Croatia and Poland were combined into a single cluster. Okay? Very early on, Belgium and the Netherlands were combined into a single cluster. They were combined because they were very similar with respect to those 10 variables. Now, unfortunately, what happens when you use the nearest neighbor method is that if you have outliers, for example, Qatar here, it ends up not being joined to any other country until the very end of the analysis. Okay, this here shows that when Qatar was finally joined to the rest of the world, it was a very large distance away from the rest of the world. Reason being that Qatar had such a low percentage of females. Well, it wasn't just Qatar either. It was Venezuela was one of the last to be joined. Singapore was joined very late. Luxembourg was joined very late, and so forth. This is not giving me a very nice separation of countries into a bunch of different groups, which is really what I was hoping would happen. On the other hand, if I go back to the analysis options and ask it to use Ward's method, okay, and then I'm going to rescale this a little bit. Okay, there we go. You see that Ward's method behaves quite a bit differently. What happens actually at the last step of the cluster analysis, if you use Ward's method, is that this group of countries here is then joined to the rest of the world. The step before that, actually, this large group of countries right here, I think you can probably see them here, was joined together with this group of countries. Well, if I decide to stop after 3 clusters are formed, then I'd have 3 very nice groups. I'd have this group here, I'd have this group here, and I'd have this group here. And I'm actually going to go back to the analysis options and ask it to create 3 clusters for me. So I'm going to tell it stop after 3 clusters. And now you can see 3 nice groups of countries that have been created. A group here, a group here, and a group here. Okay. I have found for this particular data set that Ward's method gives me what I think is an intuitively nice collection, separation of the countries into clusters. Okay. Well, now let's look at a couple other plots that might be of interest. Here is a 3-dimensional scatter plot. Okay, and now it's color-coded, each country, each point represents a country, according to which cluster it was put into. Now, unfortunately, I can't plot versus all 10 variables. I can only plot versus 3. That's not a very good separation, unfortunately. Population density, rural population, and female percentage don't really show you why those countries were divided the way they were. On the other hand, if I go to pane options and ask, for example, for the infant mortality rate, the rural population, and GDP per capita, you begin now to see what the cluster analysis has found for me. Okay, there are a large group of countries down here with low infant mortality and relatively high GDP, which define the red group. There's a group of countries down here with a fairly high rural population, low GDP, high infant mortality that define the first group, the blue group. And then a middle group of green countries right here. Now, I'm going to show you in just a moment how I discovered and figured out which variables would be interesting to use on that 3-dimensional plot. Okay, there is a method for doing that, which I'll show you in a moment. Before I do that, though, I'd like to show you a couple other diagrams and plots that you might find interesting if you're doing a cluster analysis. One of the interesting plots that I like, at least if I don't have too many observations, is something called an icicle plot. An icicle plot will show you for each country in the data set what countries belong to what groups when I have 3 clusters, 4 clusters, 5 clusters, 6 clusters, and so forth, all the way up to 62. Now, the way you read an icicle plot is you start, for example, and you look here where it says 3 clusters. Any countries in the column labeled 3 that have an X next to each other are in the same group. So if I scroll down, for example, I'll see that there's a whole bunch of countries here, all the way down to Swaziland, which are in one group once I've gotten down to 3 countries. Albania, on the other hand, starts the next group. And then you have Albania, Romania, Bulgaria, and so forth, all the way down to, where is it? There it is, Samoa, which ends the second group. And then the third group is countries like Austria, Switzerland, Germany, and so forth. Well, by looking at the X's, you can actually see who belonged to the clusters when there were 3 groups, when there were 4 groups, when there were 5 groups, and so forth. So, for example, if you look right up in this section here, you see how there's a break. The group of countries Angola, Chad, and Zambia were combined with Ethiopia, Kenya, and so forth at pretty much the 20th stage when we were being reduced down to 20 clusters. So by looking at the icicle plot, you can actually see what countries are in what groups, when they got combined, what the groups were when they got combined, and hopefully learn a lot about your data from looking at that plot. Now, there's also something called the agglomeration distance plot. The agglomeration distance plot shows you the distance between 2 clusters at each stage of the hierarchical analysis. That is, when the countries are combined, the clusters are combined together. And what we would expect to see if, in fact, we have divided the countries into a natural separation is something very similar to this. A slowly, exponentially increasing distance without big jumps. If there was a big jump in the distance, for example, here to here, it might mean that we don't have enough clusters. But if we see an exponential sort of increase here, it means we've probably gone far enough in terms of dividing the observations up into groups. Okay, and I'm quite satisfied in this case that 3 clusters is a pretty good number to look at. Okay. All right, well, now, at this point, I want to show you how I decided what variables would be good to use on this particular plot. I did it by first going to the analysis toolbar and asking to save the cluster numbers. What that just did is that put into Data Book B the numbers 1, 2, and 3 for each of the countries that had complete information. Okay? Now I'm going to go take these same variables that I used for the cluster analysis, do a Control-C, and now go to Relate on my top menu to Classification Methods and do a discriminant analysis. Okay, now a discriminant analysis will let me take these variables and will help me decide which of the variables would be useful in identifying what cluster each of the countries belongs to. At this point, I have the data, you see, the countries divided into 3 groups. But I'm not really sure which of the variables distinguish between the groups. But a discriminant analysis will help me do that. And in fact, I'm going to go ahead, take the various defaults in my discriminant analysis. And what the discriminant analysis will do is it will come up with two what are called linear discriminant functions. Two linear combinations of my 10 variables that best identify which cluster each of the observations belongs to. And you can see, for example, with the first discriminant function here, that one particular linear combination of the variables does a very good job of telling me which countries would be in the red cluster, which countries would be in the green cluster, and which countries would be in the blue cluster. It's a very powerful discriminator amongst my countries that identified my different clusters. Function 2, you can see, does also sort of contrast the green countries, which are a little high, to the red and blue countries, which are a little low. Okay, now that's good. What I need to do, though, is I now need to look at those discriminant functions. And in particular, I want to look at this table right here, in which it shows what are called the standardized discriminant function coefficients. Basically, these are the weights associated to each of the 10 variables in my cluster analysis after I've standardized them, after I've divided them, subtracted out the mean and divided by the standard deviation. And what you should be doing now is you should be looking in my table for those weights that are large. And you can see right here that the largest coefficient on both discriminant functions is for the log of infant mortality. So the single variable which was most important, it appears, in placing my countries into different groups, into different clusters, was infant mortality. Okay? It wasn't the only thing, but it is clearly weighted the highest. Now you can see there are also relatively large weights on infant life expectancy, which of course I think I showed you already is highly correlated with infant mortality. There's some pretty healthy coefficients on fertility rate, and also, this was a little surprising to me, on consumer price inflation. Consumer price inflation seemed to be a variable that the cluster analysis relied on to do groups of clusters. Okay, now what does that tell me? Well, that tells me that I now might want to go back to my cluster analysis and use those important variables to create plots. So I'll go back to my cluster analysis and let's look at the two variable scatter plot. Right now the clusters aren't very well defined, but if I click the right mouse button, go to pane options, and ask, for example, to put life expectancy on the x-axis and infant mortality on the y-axis, you can see there's a very good separation between the groups. Oh, incidentally, it's plotting 3 colors for the 3 clusters. Then there's a little plus sign at the centroid of each of the groups. The centroid is the location of the means for that particular group. So here's the centroid for the red group, here's the centroid for the green group, and here's the centroid for the blue group. Another nice plot here using some of the other variables is, let me see, age dependency ratio. That's what percent of the population are dependent on those working versus, I thought log of GDP was a pretty interesting plot too. Okay, here you can see 3 groups of countries, and they are pretty well grouped by GDP. And the age dependency ratio sort of contrasts the blue group with the green and the red groups. Okay, so the lesson there is that the discriminant analysis is very useful for helping identify what variables were most important in determining the clusters. Okay. And again now, this was all part of the hierarchical, the agglomerative hierarchical clustering method. Now, there's a second method of cluster analysis that has become very, very popular in recent years. It's called the method of k-means. The method of k-means is somewhat different than the hierarchical method. Rather than starting with n clusters, 141 clusters, and combining them step by step by step. In the case of the method of k-means, you actually start with a small number of clusters. For example, you pick 3 countries, and in a moment I'm going to pick the United States, China, and India to seed my clusters. You then take all of the remaining countries and put them into the group associated with whichever seed they're closest to. So some countries will get put with the United States, some will get put with China, some will get put with India. Okay? After you do that, you calculate the centroid of each of the clusters. Again, the centroid is the point in 10-dimensional space that's the mean of each of the 10 variables for that cluster. If you find any observations that are closer to the centroid of a different cluster than they are to their own cluster, then you move them to that other cluster. You then recompute the centroids and you repeat until nobody is closer to the centroid of a different cluster than they are to their own cluster. It's called the method of k-means. Now, it's easy to do in Statgraphics. Let's go back to Statgraphics. All I need to do here to switch to that is push the right mouse button, go to Analysis Options, and tell it I want to do the method of k-means. Now, you'll notice on the Analysis Options button, there's also a button called Seeds. This is the screen now where I want to tell it what countries to use as seeds. And I need to do it by row number. Well, I've already figured this out for you. I know that the United States is in row 176. I know that China is in row 33, and India is in row 78. So I'll put in the row numbers for those 3 countries, use them as seeds, and it will now apply the method of k-means. And I think you can see that things changed a little bit. In fact, I'm not sure why this country, this blue country over here, is where it is. It seems like it should be back with these. But according to the method of k-means, it grouped the countries this way. Now, you're limited a little bit in the types of output you have when you do k-means. Certain plots like the dendrogram aren't available. They don't make any sense because you didn't start, for example, with 141 clusters and combine them. You can still get scatter plots, but things like icicle plots and dendrograms, they're not available. What is available, though, are some summary statistics. If I go to the analysis summary and I look at this section right in here, you will see some information about the different clusters that the method of k-means created. it created 3 clusters. The first had 60 countries in it. The second cluster had 43 countries. The third cluster had 38 countries. Okay. You can also see the means or the centroids of the 3 clusters. And if you can look at these numbers, you get also an idea of what variables were important in defining the clusters. For example, if you look at the rural population, that's sort of right in here, right? Rural population. Cluster 1 averaged about 40% of people living in rural areas. Cluster 2 averaged 64% in living in rural areas. Cluster 3 only 24% in rural areas. So there's a huge difference between the clusters in terms of what percent of the population lives in rural areas. There's also a huge difference in consumer price inflation. Look at this. About 4% in cluster 1, almost 7% in cluster 2, and only 1.3% in cluster 3. So if you look at the centroids, you get a pretty good idea also of how my various clusters are defined. And then looking at this data, and I've looked at it quite a bit, an interesting scatter plot of this data, well, it's the same one that I've done before. It's infant mortality on the x-axis, rural population on the y-axis, GDP on the x-axis. You see pretty good separation with respect to infant mortality. Not quite as good separation on rural population, although you can definitely see the means are different. But also, if you look at the vertical location, you see the clusters are differentiated by the log of GDP. Okay, now I want to show you one additional plot. This plot is not currently available, but will very soon be available. It will allow you to actually take the cluster numbers, save them away the way I just did to do the discriminant analysis, but then easily display them on a world map. The current version of Statgraphics only allows you to create maps using a couple simple map formats. We'll soon be releasing the ability to create maps using any shapefile. And that's going to actually greatly expand the different maps that we can create. I just wanted to give you a little preview and show you actually how Ward's method did divide the countries into groups. It's a very useful way of looking at the result of the clustering. The red group in this case, which was the group seeded by the United States, ended up with the US, Canada, most of Western Europe, New Zealand, Japan, and a few other countries around the world. The blue group was the one seeded by China, ended up containing the USSR, Russia, and so forth, some of the countries in North Africa, and most of the countries in South America. Then there was the green group. The green group was seeded by India and ended up capturing most of the other countries in Africa as well as one of the countries in South America. The countries, incidentally, which are white, like Australia, did not have complete data. So they were not able to be grouped into particular clusters. Missing data can cause you a problem, of course, in trying to determine clusters. So that is the result of Ward's method in terms of dividing my countries into 3 different clusters. And it's an interesting data set. I'll be making the data set available to you all later today So if you want to work with it, you can. And finally, a last slide. The reference I like that I've used over the years to tell me all about cluster analysis is a book by Johnson and Wishern. Now in the 6th edition, it's called Applied Multivariate Analysis. I will be putting copies of my PowerPoint slides and also my recorded webinar here, the recording of the presentation, at www.statgraphics.com/webinars sometime this afternoon. Okay, that is the presentation that I put together, which I hope gives you a good idea of what's available in Statgraphics to do cluster analysis. Now you can do it on much larger data sets than I did. I wanted to do something that generated a lot of nice graphs so you could understand what was being done. It's definitely possible, though, to handle considerably larger data sets. All right, I'm handed here a list of questions that have been sent to me during the presentation. It's not too late if you have another question to submit it through GoToWebinar. I'll take a few minutes now and talk about, respond to these questions. First question is an easy one. Where can I download the data set in PowerPoint? And there's the link right on the screen right now. Second question, is there any relation between determining the number of clusters and the number of factors in a factor analysis? I would not think so. You could basically, for example, have just two factors, but certainly have multiple groups in the space of those two factors. I mean, you saw, for example, in my discriminant function, okay, that the discriminant function suggested that you could pretty well discriminate based upon two linear combinations of the variables. I'm trying to go backwards here. And yet it definitely gave you three groups. Here's the one I'm looking for, I believe. No. So no, it's definitely possible to have more clusters than you have either variables or significant factors. Because the groups, the way to think of it is you're in a p-dimensional space. But groups or clusters are groups of points close together in that p-dimensional space. And p might be 3, but you could have 6 groups of points in the 3-dimensional space. So my gut feeling, and I hadn't thought about this, is that the number of factors in a factor analysis and the number of clusters are showing you different things, telling you different things. There's a question, what does the system do with missing values? The system right now is excluding any cases that have missing values. It's basically taking any countries that have missing data on any one of the 10 variables and excluding them from the analysis. So a country for which we didn't know the inflation in 2009 is unfortunately not included in the cluster analysis. And there are no other options for really doing anything else. There was a question, would you repeat the explanation of a centroid? Okay, well, in any particular plot, and this, for example, is the plot of the discriminant functions, it could be a plot of the variables, you see 3 groups of points, and you see a little plus sign at what I said was the centroid. The centroid is located at the mean value of x and the mean value of y for the blue points. This centroid is the mean value of x and the mean value of y for the green points. This is the mean value for x and y of the red points. When I talked about the centroid with respect to each of the 10 variables in my cluster analysis, the centroid is a point in 10-dimensional space located at the mean of each of those 10 variables for all the points in a particular cluster. So just think of the centroid as being located at the point where all the variables are at their means. Okay. Well, those were some of the questions. I think I see some others coming in. Chris, do you have a few other questions here? If you want to wait a moment, Chris is printing out another list of questions for me. Oh, this is a relatively long list. Question, what is the benefits of k-means clustering over the hierarchical methods? That's an interesting question and one I don't really know the answer to. One of the interesting things about k-means, of course, is that you can direct the clustering to some extent by seeding it initially. You know, so if you were a credit card company and you knew what a typical reliable person was and unreliable person was, based upon various characteristics, you could start the clustering off with a typical person that's a high credit risk being one cluster and a person that's a low credit risk and being another cluster. And the initial step in the algorithm will be to group everybody together, some of them with the low credit risk and one with the high credit risk. And then it will start to exchange people, but it will end up typically, if you seed in that way, with two clusters, which we would expect to give us low credit risk folks and high credit risk folks. So I can certainly see that as a benefit, the ability to actually seed it with individuals that you want to start with. You could see in some of the clustering that was done, for example, the nearest neighbor clustering, that the outliers weren't really combined with any clusters until late in the algorithm. K-means is likely, I would suspect, to give you some more balanced clusters than you get with some of the hierarchical methods. It's an interesting question, and I have to do a little bit more reading because I'm not sure exactly what all the benefits are. I know, though, that k-means is very, very popular, particularly on large amounts of data. So a lot of folks must have found that it gives them fairly good results in working with large data. Another question, can we do k-means and then hierarchical clustering on the centroids and get results showing observations? Can we start with k-means and then do hierarchical clustering on the centroids and get results showing the observations, like get a dendrogram or something like that? Well, I mean, you certainly, when you're doing k-means, I mean, part of the output is clearly a plot of who's in which clusters. The only things that you're really losing when you do k-means is you're losing the ability to see the dendrogram, which tells you when two clusters were combined, and the icicle plot and so forth. which really makes no particular sense if you're doing k-means. Right, and regardless of what method you use, you can create a map like this or a scatter plot or whatever that does show you what observations belong with each cluster, which guys go together, which countries are different from which others. So that's not really a disadvantage of doing k-means. What you don't see is the combining of the clusters in something like the dendrogram, because that's not the way k-means works. There's another question. We get this question almost every webinar I do. Can we install Statgraphics on a Mac? Okay. There is not a native Mac version of Statgraphics. Okay, however, there are a number of Windows emulators that will run Statgraphics quite nicely on a Mac. Chris actually knows more about exactly what emulators are particularly good than I do. There is not a native version, but we do have a lot of people running Statgraphics on a Mac using a Windows emulator. And that's the only way to do it at the moment. Is there a convenient way to tag observations, show labels on a scatter plot? Absolutely. I guess I didn't do that, did I? If I have any particular plot in Statgraphics, I can, let's say, take a two-dimensional plot like this. Oh, I wonder who that blue point is. I go up, I push this button on the toolbar, the Identify button. Tell it I want to identify by country and tell it to click point to label. And then when I click on a point, you see the label of the country. So there it is. It's Qatar out there with a, well, not really looking like it belongs with the other blue countries. But the reason it's so different, as I told you, was the low female percentage. So yes, it's very easy to click on points and identify them. Very, very useful when you have things like outliers. It's this Identify button. If I did that too quickly, it's this Identify button on the analysis toolbar. It sets it up so you can just click on a point and identify it. A question, can neural nets be used in Statgraphics for clustering? Not currently. We have not implemented that. Perhaps through the R interface that we have, you could do it, but there's nothing native to Statgraphics that would let you do that. If you haven't seen my webinars on using R from Statgraphics, we have set it up to make it easy for you to take data from Statgraphics, push it off into R, at which point you can use various algorithms in R to do your calculations and pull the results back into Statgraphics. So it's possible it could be done through the R interface, but there's nothing native to Statgraphics to do that. Okay, are there similar procedures which apply to variables as opposed to observations? Yeah, you can cluster based on variables the same way you can on observations. That's particularly useful, would not be very useful in this case, but if you had lots and lots and lots and lots of variables and you wanted to find out what variables were similar to one another, you could do the clustering on the variables rather than the observations. Why was Australia not grouped? Because Australia had missing data on certain variables. If I look back in the data book and look at the World Bank data, Australia is here. It must have been missing data on something. What was I using that it might have been missing data on? Trade. Yeah, right there. As you see the missing value right there. If I hadn't had trade in the analysis, then we would have been able to use get Australia. And since trade was not particularly important, if you want to try it yourself, try taking trade out and see where Australia ends up. Someone sent me a comment that you should think about, if you're trying to think about what the centroid is, think about it as being equivalent to the center of gravity in physics. It's the center of gravity or the center of mass in a multidimensional space. A question, can you turn the dendrogram 90 degrees? Well, I don't think so. Let's see. If I go back to Ward's method here, can I turn? No, I can't. If I could, it would be on pane options. I guess that could be useful. Let me write that down as a good enhancement. I figured I'd do it usually horizontally because there's more real estate along the x-axis than there is along the y-axis. And you can see I brought the font size way down in order to read the countries. Question, can the cluster analysis be used for solving vehicle routing problems? I don't know. Vehicle routing. Good question. If anybody knows the answer to that, have you ever seen cluster analysis used for routing vehicles? So what you're asking me, I guess, is, I guess you must be thinking, for example, when UPS sends out its delivery trucks, how do they decide who they should deliver to? And if you created clusters in a two-dimensional geographical region, it would sort of divide the customers up into natural groups. Sounds like you could use it. Never really thought about that. Question, is there a good method for identifying good candidates for seeds in a k-means analysis? Well, the methods I've read about are basically picking good candidates using your knowledge of the process, or just randomly identifying the seeds. Part of the k-means procedure, I don't want you to think that the seeds always end up finally in different clusters. Part of the k-means procedure does switch points from one cluster to another. And it is possible that if you don't start with good seeds, that 2 or 3 seeds could end up in the final analysis being in the same cluster. The seeds just get the process started, and sometimes they do it randomly. And you might try doing the cluster analysis several times with different random seeds to see how different the results were. There probably are methods for identifying good candidates. That's another good question for someone to look up. I don't remember reading about that, but there's a lot out there about cluster analysis. Once you find the most important variables after discriminant analysis, can you run a post hoc analysis with those countries with missing values, but which have the most discriminant variables? Once you find out the most important variables after you do a discriminant analysis, could you do a post hoc analysis with those countries that had the missing values but have the most discriminant variables? I'm not quite sure I understand exactly what that is, but certainly I would think if you looked at your discriminant analysis, looked at the output of your discriminant analysis, and it was back here someplace. where we did the discriminant analysis, right? And you found out that certain variables were not important, not being used very heavily. For example, look at trade. You see right here, trade? It was minus 0.11 on the first discriminant function, 0.01 on the second discriminant function. You'd probably get almost exactly the same result if you got rid of trade, and that would bring in other countries like Australia that we just found out had a missing value on trade. So I would think it might be a reasonable thing to do if you did find certain variables that were not weighted highly on either of the discriminant functions, to remove them from the cluster analysis, which could easily then bring in some more of the countries that that did have missing variables before. That would seem to be a good idea. And at some point, when I have a little more time, I'm trying to finish here because I've gone on a little long. I'm going to see what happens if I take trade out. I'm pretty sure Australia will come back in. Well, I know it'll come back in. I'm guessing it's likely probably to be very similar to New Zealand. So I'm guessing on my world map, it's going to come in as red, but I'd like to find out. Question, I understand k-means allows large numbers of observations. Both the hierarchical and k-means procedures will allow you the large number of observations. Actually, the hierarchical clustering is faster than k-means. One of the problems with k-means on large numbers of observations is the iterative step that occurs at the end. And it can take a long time, a lot of computer power, until the k-means ends up with a final solution. I do remember reading that occurs, and some people did say, now going back to one of the other questions, some people did suggest, I saw this in one article, that if you had a large number of observations, that you start by doing a hierarchical clustering, okay? And then you take observations, decide how many clusters you want based upon the hierarchical clustering. Find observations that are close to the centroids of those clusters that you get from doing the hierarchical clustering, and then use those to seed the k-means clustering. They said that that would have a tendency to reduce the time it took the k-means procedure to find a final solution. You can imagine in the k-means procedure, if you give it bad seeds very close together, it may take many iterations until it finds good clusters. However, if you use hierarchical clustering, find good clusters, take points close to the centroids, use those to seed k-means, you're likely to get a solution much quicker. When you want to make best differentiation between groups, what methods of cluster analysis do you suggest? To be honest, I think Statgraphics makes it easy enough to try them all and to see which one gives you the output that makes most sense. I mean, there's lots of arguments amongst people about what's the best method to use. Is it Ward's method? Is it farthest neighbor method? Is it k-means? Truthfully, what makes the best method to use on any particular data set is whatever gives you the most information about the clusters. And I think you can see it's easy enough to switch from one method to another, try them all, and see which gives you clusters that are most informative, most understandable for your particular data. If k-means is used, what if the data fall into 5 distinct clusters, but you give it only 3 seeds? Well, you end up without fully differentiating amongst the clusters, which is another good reason, I guess, to do hierarchical clustering before. You could see, for example, with Ward's method, where you have the dendrogram, that you can get a pretty good idea here that there's a natural grouping of 3 clusters. If you wanted a 4th, well, Qatar is different. It's going to be its own cluster. I probably should have gotten rid of that country actually from the data set. Oh, but then again, you've got Singapore and Luxembourg also as being fairly different than the others. The dendrogram is really quite informative, though, in terms of telling you how many clusters to start with. So if you start there, you might get a good idea of how many seeds to use for k-means. Someone noted that I did linear discriminant analysis. How about nonlinear discriminant functions? Absolutely. If you want to do that, that would certainly be a reasonable thing to do. On the last question, on the dendrogram, what is the distance on the y-axis? The distance is the distance between 2 clusters when we decide to put them together. Remember, what happens is we start with 141 points in this case. Find the distance between 2 points, put them together. When we put them together, we then treat them as 1 point, essentially. And we find the distance between that pair of points and everybody else. Well, the distance on the dendrogram is the distance between 2 clusters when they're joined. And as I said before, when you look at this agglomeration distance plot, if you saw a big jump at some point, that would mean that you're joining 2 clusters very far apart and would give you an idea that maybe that wasn't a good thing to do. Maybe you shouldn't have joined them together. Okay, I need to stop now. I'll let you all either get back to work or if you're listening from Europe, go home and get dinner. Anyway, I thank you for the good attendance and for staying and listening to this. Before the end of the day, we will post on statgraphics.com the data sets, the presentation, and the PowerPoint slides. And as usual, if you have other questions that come up after I finish, go ahead, send it to either neil@statgraphics.com or support@statgraphics.com, and we'll be happy to answer the questions for you. Okay, so long.